All right, so let's see how matrices can help us with systems, and this is where we wanted to get to with what we've done previously with our matrix operations. So the first thing we're going to do is we're going to learn how to write what we call an augmented matrix based off of a system. So it works out really simply. What we do is we just make a matrix with the coefficients. We can drop the variables and just make our matrix just using the numbers that we have. So my first equation is 2x minus 1y equals 7. So here's how the reason we call it an augmented matrix is because we put this additional line in here. What we've done is we've just added on one column here to it, and that's where that's going to kind of stand for the equal sign for us. It's going to keep this part, which is the left side of the equal sign with the variables, separated from the right side constants over there. So we just have 2, -1, and we draw our vertical line 7. And then for our second equation, we have 1x, 4y, and it's equal to -2, like that. So that's our augmented matrix for this system. It's pretty simple. So why do we put them into a matrix, and what's our goal? How do we end up solving the matrix? Well, our goal is to get something called row echelon form. Instead of a 2x2, I've done a 3x3 matrix here. So imagine that this is the first equation here. We want to get that first row to have a 1 in the first position, and then we can have values. I just call them A, B, and E for those. They can be whatever you'd like. And then in our second column, notice we want a 0, or our second row, we want a 0 in our first column and a 1 in that second column. And then it doesn't matter what the third column is, and then the augmented side over there. And then here we want a 1 in that position. Okay, a row echelon form is always going to have 1s on the diagonal, starting from the top left and working down to the bottom right. Everything underneath the 1s we want to have as a 0, and then these numbers can be whatever they want. Now, why would we want that? Well, if I were to switch this back into a system, this top row would give us this equation: 1x plus ay plus bz equals e. And you think, okay, well, what is that? That's not really helpful. I agree. That in itself is not helpful. Okay. What would be the second equation? Well, how many x's are there? 0 x's. So the x's are gone. We just have 1y. Okay. I'm not going to write these ones here. Well, we just have 1y plus cz equals f. You might think, okay, that does look a little bit better, but how about this last one? This last one tells us there are 0 x's, 0 y's, and 1 z, and that z is equal to some number called g. So if we have it in row echelon form, we have just solved it for z. And if we've solved it for z, we can substitute that back in. This is called back substitution into here, and then we'll solve for y. And then once we know what y and z are, we can substitute into there and get x. So this row echelon form solves for that last variable, and we can use back substitution. And because it's in row echelon form, hey, we just substitute back into the row above and get the next variable. Then we take those two and put it back in the row above, and so on for however many rows that we have. So this row echelon form is good. Okay. So then how do we take something that looks like this, and how do we get it in a row echelon form? Well, these are the operations that we can do. They're called row equivalent operations. They're the things that maintain equivalence, that we haven't actually changed the system. We've just manipulated and created something equivalent. So we can interchange any two rows. That should make sense, because you know what? Doesn't matter if I put this row on, or this equation on top and that one on the bottom, or could I switch them? Right? I can rewrite this system as x plus 4y equals -2, 2x minus y equals 7. Isn't that the same system? That's allowed. Okay, so that's our first operation. Our second one is we can multiply each row by a non-zero constant. We don't want to multiply by 0, of course, because that would just wipe everything out, but we can multiply it by a constant. So, if I was solving this system before, couldn't I take let's say the bottom row, the bottom equation, which would equate to the bottom row, and multiply it by 2? right? We've done that solving systems. We multiply both sides of an equation by the same number. That's multiplying the whole equation, which is the whole row, by a number. Now, lastly, we can add a multiple of one row to another. I keep clicking the wrong direction here. So, what does that mean? Well, if we were to solve this without using matrices, okay, I think what we would do is we would probably multiply this top equation by 4 and add it to the bottom equation. Isn't that what we'd do? We'd multiply the top one by 4, take the bottom one, add them together, y's are eliminated, like that. Okay. So that is an allowed move with our matrix operations here, is we can add a multiple of one row to another to create a new row. All right, so let's go back to this original system from the other page. Okay. Let's rewrite it as an augmented matrix. And our goal, again, is to get it into row echelon form. Now, this is a 2 by 2. So our row echelon form is going to look like a 1, a 0, and a 1. 1's on the diagonals. This could be any number. And then these could be any numbers. So we wanted to get it to look like that. So when I look at this system, the first move I'm going to do is knowing that I want to get a 1 in that top left position. Well, remember that one of our operations is we can switch rows. So if I switch the bottom row to the top row, I'm a little bit closer. So we have 1, 4, negative 2, 2, negative 1, 7. All right, so that's what I wanted first. Now, what do I want to do next? Well, we know we want a 0 underneath it, and we want a 1 over there. How are we going to do that? So, I apologize for the sounds that are coming. I don't know how well or how much you can hear them, but they're doing some work in school today, so I apologize for those sounds. All right, so I want to get this to be a 0. And how am I going to get that to be a 0? Well, sometimes students think, well, let's just subtract 2 from everything. Well, is subtracting or adding everything into a row one of our allowed operations? No, we can't do that. We couldn't do that before when we're working with equations. Say we're going to just add 2 to everything. It doesn't work like that. Okay? We know what our available options are: to switch rows, to multiply a row by some number, and then to add a multiple of one row to another. Now, the only way I can get that to be 0 with multiplication is to multiply by 0, and that's not good. That just wipes out everything. So I want to do a multiple of one row plus another. So here's what I'm thinking. I look at the top row, and I say, if I could get this spot right there to be a negative 2, and if I added it with this one, that would be a 0. This should feel similar to solving systems like we have in the before. So here's what we're going to do. I'm going to write this as we are going to take our new row 2, we're going to take negative 2 times row 1 plus row 2. So our top row is going to be the same. Now what do we get for our new row 2? Negative 2 times row 1 plus row 2. Negative 2 times 1 is negative 2, plus 2 is 0. Negative 2 times 4 is negative 8, plus negative 1. Negative 8 plus negative 1 is negative 9. Negative 2 times, don't forget about this side, negative 2 times negative 2 is 4. 4 plus 7 is 11. All right, there's my new row 2. Okay, I'm one step closer to this row echelon form. We've got this 1, we've got the 0. Now we need to get the next one on the diagonal, which is right here. Now this is a little bit easier to do because all I have to do is multiply this row times -1/9, and that's going to turn that into a 1. Making a 0 we can't get by just multiplying the entire row by a constant because we'd have to multiply by 0. However, if we want to make it a 1, we can multiply the entire row by a constant. Let's see if I have enough room on this page. I think I do. All right, so our new row 2 is just going to be -1/9 times the old row 2. We've got 1, 4, -2. Now let's multiply everything in here by -1/9. 0 times -1/9 is 0. And that's why we want to get that to be a 0 first, because then when we multiply it by something, it's still 0. It doesn't change it. -9 times -1/9 is 1, and 11 times -1/9 is -11/9. All right, so now we have it in our row echelon form. And what does this tell us? Remember, this first column is for the x's. The second column is for the y's. This tells us that y equals -11/9. So then we take the top row and we say, okay, x plus 4y equals -2, and we can substitute in our -11/9 for this. So x plus 4 times -11/9 is equal to -2. And let's just work through this. That is x minus 44/9 equals -2. Now I know I'm going to add this over, so I'm going to get this to be in ninths. -2 is what? -18/9. So now if I add my 44/9 on both sides, we get x equals -18 plus 44 is what? Is that 26? Yep. 26/9. So there, we solved our system. Now, let's go back to this. Okay. Remember I said, well, how would we do this if we weren't using matrices? I said we'd take 4 times this plus that, and actually looking at this I made a mistake because I was going to say let's check and see that we got the same thing we would have got if we would have just solved it without matrices. Well, when we added these, this would have been, I subtracted, not added, that would have been a 9, right? 9x equals 26, so x equals 26/9, which is exactly what we got right there. Now, you're probably thinking, well, that's way simpler, way faster, isn't it? I agree. The matrices is certainly not faster on a 2x2, but I want you to understand the operations, because there's going to come a point, there's going to be a breaking point where using matrices is going to be much more efficient than just solving it with our old methods of substitution and elimination. For example, look at this one. Okay, now we're going to step it up to 3 variables, 3 equations. So in our next video, we're going to attack this problem.